Welcome back to High Performance Computing, Advanced Scientific Computing, the second part of our practical lecture 2.1. And the first part already connected quite some of the lectures we had before in our course. This was starting with Unix, then over entering with SSH into a remote HPC system, ELIA, then basically creating a C program, understanding the module environment, that basically there needs to be then also an MPI implementation if we want to go to the MPI that we learned before and do an MPI application. Hence, over the time, basically we extended then the C program that we already knew from previous lectures to something we call then really an MPI application. And we did this by entering basically the MPI header of the certain implementation in the C program. We had MPI init and MPI finalize as very important commands, basically earmarking a little bit where the MPI environment is then active, so where you can actually write the parallel code. And we learned basically two of these very important procedures or methods, if you want, obtaining the rank information. So what is the unique ID I have basically among all the other processors, and how many processors are there in the certain area of communicators. So communicators is something we addressed briefly. We had MPI com world, and we said that's the world of all the processes in this communicator. That's fine. We will learn later also in the course that there's a Cartesian communicator and that you can create numerous other communicators that serve your purpose. However, the com world is very specific because it's really the world of all of them. And we use it here in the first practical examples of MPI basically around this. Furthermore, part one was really then connecting again to the scheduling. Also, this is what we had now numerous times when we were scheduling a C program. If you remember, scheduling was a concept where we enable basically the concurrent access to many different users on the HPC machine. Hence, we firstly don't want to have users always running on the login node, because if you have 200 or 400 people all log in and all running there something, then the login node has some difficulties. And hence it is just more used to execute basically a scheduling command. We use here sbatch for Slurm, but there are other commands in other schedulers. But the idea is really to use the compute nodes and not the login nodes, what we also had in part one, by understanding that, of course, then the module environment for the MPI implementation has to be still basically give away in the job script. So we have to specify that we want to use OpenMPI in version 4, for example, what we did. Hence, the module environment needs to be specified because we're leaving the login node. Even if we module loaded on the login node and we compiled our hello world C and then later the ping pong application in part one, that was all good. And we specify this in the job script because then we going away from this node with the sbatch command using the scheduler, and we can land somewhere in our U-turn partition, which we also learned is then compute 1 to compute 4 node in our particular job example. We basically have been then on compute 2 node or compute 1 node. We first extended to ping pong. We understood that hello MPI is not really a message exchange. It was rather using the MPI ranks and the MPI size of the communicator in a way of telling us who I am, but as a processor, but or process more accurately. But then, of course, we said there was no real message sent, and we had a ping pong executed, where we learned again that the rank information can be used to steer the application logic execution. We have one particular challenge here, and this is the SPMD approach, right? So same program, multiple data. So we execute the very same executable 4 times, 10 times, 12 times. But the point is the rank information then helps us to determine different parts of this application to be executed by different processes. Hence, this was a very powerful tool then, and we have seen that ping pong actually works and that it's a very trivial application. It literally has just, send and receive and another send and receive. But this brought up the question of what happens if you now have 500 processors to communicate to, and what happens and how you want to basically program what happens, right? You could immediately think, why not doing a loop 500 times to send, receive, ping, pongs, and so on? Maybe just a ping to transfer them data. I don't necessarily need a pong. All these are questions which we will come back a little bit in the second part now of the course, because MPI provides us with a very nice set of application methods that are often used called collectives. And with this, you have different message exchange options, as the name suggests. Again, let's review them briefly. They're really different from the idea of point-to-point communications that you see on the top, mostly for the reason that you don't have to specify exactly this rank that you want to communicate to, right? You remember in the ping pong, we had the source, destination, rank specified in order to do really, a send and receive, basically of rank 0 to 1, and then the other way around for the ping pong completed. So here we're talking about messages which are more addressing communicators. So the collective communication methods really need then basically as a kind of method parameter one of these communicators, like MPI ComWorld, but you can imagine, as I suggested before, also in the review of lecture 2 in part 1, it could be for different communicators. But in our example, we stick with MPI ComWorld. Hence now, in comparison to the first part of the lecture, we don't really go into this anymore. We extend now the examples, go to this collective communication. Again, a brief review. Here we have an MPI broadcast. The goal is that you have one data item that you want to broadcast, as the name suggests, to all the other processors. Right now, immediately you can say, well, I can do this by, iteratively, just doing for loop 500 times to send it to all the other one, which are maybe given out by MPI com size, basically having my size of number of processors, and I just do send, receive all the time. And this is quite basically not really a performance way of doing it. So here the implementations of this collectives have the benefit of being very smartly implemented, partly based on tree designs and so on. That goes beyond this lecture today, but save the way with these loops and so on, and really use the collective communication operations. Another example, which is often used in practice, is that you would have in a scientific application sort of an array. Here just basically you see here data items in this array from these different elements, and then what the scatter is doing here, this is a collective communication again, where you scatter this array to many different processors. And then there's a kind of inverse operation to this. Once you maybe computed on this data, you want to have one processor, again, collecting all of this information. And then you basically have the array filled again with the different information from the memory of all the different processors in this particular communicator. Then we extend this a little bit to an idea we call reduce, mostly for the reason that you're usually also interested in having some summary statistics in applications. You would not do the reduce just for fun. You would do the reduce and gathering of information to perform something. And the idea here is really do as less as possible lines of code. Because if you think about many of these operations, you could do with doing different loops. You can, of course, in the loop of going through all the processors, almost like gather, getting you all of this with send and receive operations. Then you do another couple of lines of codes of making, again, a sum iteratively through some array. So here we're talking about that the collective communication is not only good for really high performance, it's also good for really code readability. So you basically have a much cleaner code. You have just a couple of lines really compared to lots of lines that you would need in a for loop. So hence that's not the way to do with loops. You really once again should use collective communication. And there are several other extensions to that. These are the basic ones, you would say. There's something we call all gather, that you basically gather the data from all the different processes also on all the others. I hope you have seen that maybe in the video I gave you in lecture 2. And there are certain of other operations like OR reduce, which of course does similar things now with also having this small operator included. The operator refers to the plus here, but could be multiplying, minus, or something else. The point to get away is really we want to have the application logic in science supported. That means the scientific code, let it be in Fortran, let it be in C, of weather forecast, physical formulas, let's say numerical methods, optimization methods, they all are already very complex to implement. And by having then a parallel approach to it, it wouldn't help us if we have a very complicated way as well to parallel computing. Hence, we try as much as possible of keeping the parallel code already also readable, also basically in a way understandable, because it will be always, let's say, mixed with physics, mixed with maybe machine learning elements, which makes the code not as easy as you see here, right? We're talking here about toy examples, where, it's very obvious that here this interesting area with 18, 19, and 6 will be, kind of filled from all the processors and so on. We have just a couple of cores, which are here 10 processors, maybe doing something in MPI Com world. Think about larger applications. Think about really complex physics code, why we really actually need this. Coming to basically then the idea of the identity again, when we, basically now changing again, so to speak, in the next step, all the initial steps will be the same. It will be basically a C program you already know. Then we added this with MPI. And here's another example where you would now thinking about what to do in terms of a collective operation. We would do the same as we did before of obtaining our com size and com rank for the application, because it's useful also in the most applications. Here, what we do is one particular element in order to understand also that we are again doing distributed memory, right? And this refers a little bit to basics in computer science, but you have learned something like the variables, and they can be undefined, right? Like when you do here an int buffer 4, for instance, this is what we call not initialized. So there are 4 different integers. That's what we know in this buffer, but there's not a particular value in it. And hence, when you just use this will be, let's say, lots of values that we can't really determine. Hence, we see here that what we want to do is that in order to show that broadcast really works, right, in one respect, we do here that only the rank source from this broadcast later will be initializing this array. So this has nothing to do with MPI yet. This is typical computer science programming C. Basically, what we're talking about is that we initialize a buffer here, where MPI thinking and parallel thinking comes now in the way, right? This is that only the first rank is doing it. Think about the same application will be executed twice, 4 times, 10 times, 12 times. I don't know. My job script will tell it. But the point is that we always will make sure that at least the source of the broadcast will initialize the array. And we see it's a for loop with an integer e, so it will actually just use a for loop index, so to speak, to initialize the buffer. But that's not the most important point here. More important is really only the source has an initialized array, basically, or buffer as we call it here. And then, of course, the interesting thing is for all of them, you see here's no if rank. Here's another example of using ranks and not using ranks. Here now this is executed by everyone. So everyone has to go out and basically, give out the buffer. Hence, what we want to achieve now in this simple example of using broadcast is let's use that in order to initialize the buffer and send it to everyone, right? And this is another example where you can think that this is often done when you have different physical applications. And you basically can see that some ranks doing other work also. And this is an example that we had with the water, but also with a race car before. When we want to simulate something over time, still maybe at the time 0 time, one of the cores decides to distribute some important data around it. Let it be the heat in the room. Let it be basically for the race car, the velocity of the race car in the moment where we want to simulate. Whatever it is, the physical variables are very much in line what we do here in order to distribute this information out to all the different processes to do something in parallel. So let's extend this, and you see that this is quite actually easy, right? So instead of doing for loops again, what we could do here, similar like the buffer and send and receive and going through this and compute this in a very, let's say, not nice fashion, we see that the broadcast just needs a buffer that we have now initialized for essentially the source, but it's not initialized for the others, right? So it's just for the one, rank 0 that is starting all of this. Then we know that this is basically the count, so the number we specified here before, it's 4 items. We need to know that they're of type integer, 4 types coming in from the source. So this is an important factor in this kind of element, which, so to speak, decides now that rank 0 is, doing the broadcast while other listen automatically, right? No need for receive, because here we specify that it should be one source and all others listen. All others in the specific world of communicators only, right? If you have now different subgroups and you say instead of MPI com world only communicator 1 or communicator 2, then this will be basically a different element. The broadcast will not reach, let's say, if you specify communicator 1, the ones in communicator 2. This is only possible because we specify MPI com world. Hence, important again, you see that instead of iterative send and receive, and you can share you one of the cool examples from practice again, that this is heavily done. Instead of using now lots of send and receives in iterative loops, broadcast and all other collectives might be very valuable, as I told you before, but you can also see that many application scientists in the, let's say, machine learning communities or physical communities, they are trained as physicists, they are trained as machine learners, AI people. And while that is, of course, very valid because it's a complex topic on its own, you see again in the codes that actually does these things, which I just described, iterative send and receive. One example you see here from our own research was PSVM, a support vector machine in AI that was on source code a long time ago. We took it in our hands, and you see here one basically publication again, which we used in remote sensing for this SVMs to really make it better scalable. There were lots of problems in the code. While the general idea of PSVM is very good, the parallel implementation of it was, let's say, something we had to improve, right? So there were these statements of send and receive. We added collective operations. There was something with load balancing, another topic which come up in lecture 3. So how you crunch down the domain, how you basically avoid memory problems. That's all something coming more in lecture 3. But here you see that really there is a need for parallel programmers that know these things, even if it's a more or less simple element now with broadcast. But you can imagine that when it comes to all reduce operations, this is again often done, that people obtain now from different processes the results with gather, and instead of using reduce directly to do a sum, they once again go through all the array elements and take a sum. So knowing about some of these methods could be very useful. And also for the readability of the code, you see it's crispy and small. Essentially what we see here is more or less one line of code, right? Instead of a bigger for loop and so on. Now, talking about this, I think it's time to dive into the practice. So let's see, because we have a practical lecture, we don't want to talk too much with slides here. Let's see how that works in practice. For that, we have already prepared in our set of applications a broadcast here. And what I will show with broadcast is very, very much in line what we also have to do with gather and scatter. So I don't want to demonstrate this today. Hence, we look firstly into our broadcast, C operation. And this is the one we just talked together about. So basically, we have the init, we have the finalize, very important. Then you basically have the buffer information of 4. We have the source saying rank 0 should be the one doing it. Hence, we have an if statement. Only if the rank is 0, then you essentially initialize the buffer here. and all others would have basically an uninitialized buffer. But the beauty is we do an MPI broadcast in between, so we assume that the buffer will be now broadcasted, in other words, sent to all the other ranks from the source, and we said the source is a 0, and this is also the rank that already initialized. Hence, everybody will get the initialized buffer from rank 0 and will be able to have a proper output and not something which is very strange and looks very weird in the output, right? So you see essentially what we had on the slide, so nothing strange there. So the same statement goes now. We have to have our modules. We have a C operation. We have an MPI implementation. So we need something. And what I will do here just now to show you is the arrow up, right? It's a very powerful tool in our HPC environments, usually giving you the opportunity to go through the history of what you have submitted. And one of it might be exactly the command we need for the module load MPI implementation. So this is equally valid if you do module avail, look in all the available modules, and then of course do this rather manually. You don't have to do the arrow up button, but I want to connect to some practical elements because you also have to do soon your first assignment. So and then it can be good to do this module load and then looking up and understanding that. Now, having done this and knowing we have a C basically code here, we can of course use our MPCC that we already know now quite long. I do again the -O to steer a little bit what the output should name of, and there are no errors in the compilation. So hence our broadcast is an executable. Again, think about the access here, but again, we also know we don't want to do this, right? Executing it on our own path or so. We want to use a job script. Hence, we have to need a job script. And this is now a bit interesting also for another reason we previously also a little bit talked about. So firstly, the job name is there, broadcast, okay, no surprises there. Partition U-turn also clear. Now we have number of nodes like 4. Right, that means we have 4 elements in the buffer, and it will be transported to 4 different, MPI tasks, which are running on different, basically on this nodes on different CPUs. So, and we use the MPI broadcast. We also load the module environment here that we need, again, remembering that we are on the login node where we now load the module. So what is actually happening here is only valid because I am on the login node, right? Again, connecting it a little bit with the point that you see here and there on the slide, which is here on the next slide and slide 25. We want to do this when we do it from the earlier login node, again, addressing these compute nodes here. Hence, when I do module load here, I can compile, that's fine. But when I do sbatch, the scheduler has no idea that we used before module load. Hence, it's good to put that in a job script so that firstly, this executable will be now, because we had 4, put on 4 different, tasks in the system. And then basically all of these different node parts in this compute nodes will then getting the information that we need this specific module to load. Hence, the environment will be prepared. Equally is true that the MPI environment will not now know that the number of tasks we have available, number of processes that work on this in parallel is 4, because basically that's what I specified here. So hence, very similar like we had before with hello world and so on. But now the difference is that, of course, we have now message exchanges, right? Like the ping pong, but there we basically had specified rank 0 and rank 1 explicitly. Now what we achieve here is now we have said we are doing a broadcast, and we send an array of 4 to some others. And here, for the simplicity in the moment, we say, okay, let's involve 4 to do that. So how that will look like, you can already imagine. So let's fetch it, submit. We get a job ID back again to show you the SQ. It's so fast that it's not in the queue. So it's literally going in the queue being computed so fast that it's directly out, so we don't see it. But the good news is we should have some output of this job ID. And we see here the number, job ID. That's also very important. Remember to have really the link to the different outputs. And not surprisingly, when we now go into the specific output of the job, having the same job ID, we now see this buffer. We also see with this that apparently the broadcast work because we have good numbers showing there, right? From 0 to 3 for all the different, let's say, 4 processes that wrote it out, right? So this is a beautiful finding. So one example why broadcast must have worked. And basically we can now see an interesting element like we had a little bit with this hello application that even for broadcast, we can now thinking about extending this, right? So let's see what happens when we do it with 8. And you know, I don't recompile the broadcast C now. All I do is just submitting it again, right? And we have another job ID, obviously. Again, it's so fast that it's not really visible in our queue, but we have an output of the job that is here. And again, from the size, you can a bit, let's say, see already we had 4 before, now it's double the size. Apparently, we can understand probably that this was now executed 8 times, meaning we had 8 different processes involved. We can get more different information about the job again. If you say this command I had already in part 1 a lot. So with the job ID we have here to learn again what was happening perhaps. And you see number of tasks is 8. As we specified, we stay in the node because we just had one node specified. Some example of getting some job information. Another part is what we want to address now a little bit more is to understand the runtime. And this is basically explained when you look again in the job script, in the job output here, or the detailed job output in a way, you see it was literally running for 2 seconds. So in the moment where I put SQ, this command and so on, oh, sorry, then it's already over, right? So basically it's so fast that we don't see anything. Now, there is a command in time there you can specify basically also how much scheduling time you probably need. We were referring to this at the beginning when you talked about scheduling, and we referred this to this particular element. So firstly, I mean, this is all documented what I showed, that you can change the C code and recompile it to 8 or 12 without the need to changing the C code or recompile, right? So we really do it just in the job script. That was the main takeaway message here. So that's the scalable code, as we would call that. And that can be quite nicely if you have bigger applications. Of course, here just giving something out that we received with one broadcast is not rocket science, but you can imagine this can be used in many different applications, especially being scalable, not knowing yet how many actually processes you really involve at that time. Now let's look a little bit again to something we call the wall time, right? So this is a more loaded discussion. That's why we have now really reserved again 10 minutes for this. Firstly, because we want to understand the SQ. Secondly, we want to understand again that in order to steer the schedule, right? You see that here. If you remember in the scheduling lecture, I was telling you that these are all the different jobs running on the machine, on all the different racks. Here, the example of Jubels, not Elia, but it doesn't matter. The same principle applies for Elia. It has different racks and the jobs are running on different CPUs in these racks. Now, what is important is the schedule, right? And you have a sort of timeline in this. So we said there's first come, first served. That means the first that actually submit a job usually also get then the time before someone else submitted later. Now, this might be true. Sometimes we actually do something called backfilling when there are scheduling holds. So if you know already, let's say that the schedule will be broken for 1 hour because we can just not fill it in the amount of processors for all the other users, but you would gently fit in, let's say with this 20 seconds job, yeah? So this is something we had in one of the lectures, that there are many different SBatch commands. We extend now our examples here our hello world to an hello sleep example, and include now this time element. So this stands for hours, minutes, and seconds. And this will inform the scheduler of how long your job will gonna take, roughly. Now you can imagine in an application with physics, not knowing it, or with a new domain in AI, having new data, unseen data you never worked with, this could be a loaded question, right? So you maybe never know really how exactly the job will take, how much time. And surely the 20 seconds again are here dedicated to the small example of hello sleep. But think about that. This, of course, can inform the scheduler and say, well, if you have a very small running job, like here 20 seconds, we can actually schedule you right now because your amount of nodes are also very little. Hence, something which you basically can see and then quickly do in order to update then the schedule and get you backfilled. Hence, we want to do this. And I think here's a little bit an old-fashioned, an old part of the job script. So sorry for this. We see this now in the practicals as an updated one, essentially when we go to hello sleep. So let's tackle this one by one. Firstly, let's understand hello sleep. So this is a hello world application I modified for a particular number of sleep seconds. Let's say this would be 120 seconds I want to sleep. Why I want to sleep? I want to basically have an operation that is not so fast like broadcaster, that we see something in the queue and that you actually can see an application that is running against the wall, as we would call it. And this is basically showing you how that works. So we have firstly now the idea that we want to sleep here for 120 seconds. We have a typical MPI implementation. We just say, you know, for rank 0, how many sleep seconds I really think about. And of course, then I say, I'm that and that processor, and then I go to sleep now, right? And then I sleep, and this will be executed by all the processors. Hence, basically, all of them will do nothing in a way, sleeping for 120 seconds. And when I'm achieving that I waited so long, then I will just give, you know, another message out and say, I just awake now, that's it. Now, what assumes is that our job must be at least running 120 seconds, if not a bit more. Right? So hence, this will be the runtime of our application as an example. Usually it would have some estimates in practice, right? So to show, okay, this will be so much and so on. I repeat the steps you already know, compiling it, basically using the history here, module load, and then I maybe do MPICC, hello sleep.c -o, hello sleep. No errors, and I have a 120 seconds sleep incorporated. Hence, I have an application that it runs at least 2 minutes. Now, when I submit this, let's see what happens when I now would say, okay, I want to have it on one node, I want to have 2 tasks sleeping. That not really matters, but this fellow is now loaded. I say this application should be terminated after 20 seconds. I just gave 120 seconds in the application. Now I say to the scheduler, please terminate it after 20 seconds. So hence, this would be stupid to do in a way, but I want to show what's happened to you, right? And this is an example where you can see that a job that is running, firstly, will be visible in the queue. That's what I wanted to achieve. So finally, you see my job running after all these lectures in the so-called queue. You see the time nicely here that we basically come up to something 15 seconds, 16 seconds, right? It's quite nicely and you can follow it. It's still running. And now we go over 20 seconds, 24 seconds, and so on. And basically see we are on compute 2. So when we look into this and in the output, more hello sleep, so more in the output here, some elements will be not really out there. So I am 1 going up to sleep, I am 2 out of sleep, and so on. So when I go here, I will see that essentially in SQ, my job is still computing. Now, this is something what we want to understand from a certain perspective, because we said, okay, submit job was hello sleep. Hence, there could be the point that this executable was essentially already existing. So what's happening is that we remove hello sleep and we do essentially our C code, and we see vi hello sleep.c, and where we have 120 seconds in, that should be there, right? So let's do this again. But some of you already noticed what maybe was happening. So in the end, we have the environment here already loaded, so we just have to recompile it and see. And in the output of the job here, we have now essentially that we are running against the wall, right? So even if our job says, okay, he was running a bit longer in a couple of seconds more long, it takes some time to run 20 and then gives a terminate signal out. So this was not going to working, right? This is the so-called running against the wall, because we had 120 hard-coded sleep, but the job script just said, around 20 seconds. And then the whole cancel process takes some time. And then we basically see that it was not really working. Now, when we do this, and we have 120 incorporated, we have this, C executable again. If we now do this again, and we would basically say, hello world, do this basically for, let's say, 3 minutes here, it will work. But I don't want to waste 3 minutes here in our, basically lecture. So we show it the other way around, that we basically just go very quickly to sleep when we recompile now the hello sleep.c, right? I think many of you now realize what happens. So if you say here, we want to, change this very quickly to maybe just, sleep seconds would be only 20 sleep seconds. So the application will be, so to speak, very quick. We recompile the executable here again, and then VI submit. Now we have a 20-second job. And if we say, okay, we just give him, say, 0 here, and we would wait really at least 2 minutes. That's what we can afford, but we don't need to, right? Now we can hopefully see that the job is now running and finalizing with the awake. So of course, this is something which, with large applications, the exact sequence here and there, something we have almost not a control in, and it looks like it, but the whole MPI environment also needs some time to shut down it, to basically put it out of the queue and so on. So there's some management overhead with it. But here you see essentially that in this new execution, we already basically have here this just away now. So here we finalized the job, which was very quick in 20 seconds. So basically something very quick again. And with this, we can be saying that essentially 2 things. You firstly have seen the job that are longer in the queue, but also we see that this running against the wall, and I've also documented to you this essentially here. Again, the job script is an old one. Sorry, you have seen it here in the practicals. It looks a little bit different now when you have this example, VI submit hello job. You have here our ordinary nodes and number of tasks per nodes, right? So this is an important factor too. Hence, to work with the scheduling a bit more accurate and more better, it makes sense to use this time command that you have learned here today. We are, of course, in the Utun cluster a little bit more relaxed. You see also here the documentation, the job is running 6 seconds already and so on. And essentially here you see that the job was running against the wall. It was canceled from the schedule because essentially you sleep longer than your job script allows. Another job example might be the S-cancel, and you can go on and give you more practical example. S-cancel is that once you see that your job is maybe doing outputs which are not really useful, you can also cancel your job, right? Something we also didn't talk about it, so it will be out of the queue and so on. And you see also nicely that some others here really work longer on these systems. Here's one user that actually have a long running job, not our 20-second jobs, but here we talk about hours and days and so on. But yeah, I think that's all what I really wanted to leave here in this practical lecture. We will, of course, come back to this, and in your assignment, you will also get really work in practice with it. So next time we have lecture 3, where we talk much more about domain decomposition and parallelization fundamentals, but we will firstly discuss your assignment then tomorrow. So see you next time.